In this last video, I'm going to demonstrate the use of GLADDvu to globally fit PGP data. The data sets are shown in Figure 6 of our Journal of General Physiology tutorial, and the results are shown in Table 5. Okay, so I've already opened up GLADDvu. I've loaded in the 10 PGP data sets with different substrates bound. I've truncated the last 500 nanoseconds of data, and I've gone ahead and fit the data globally to a model that uses 3 Gaussians, in which we have selected that not depth, background, and amplitude option. So if I look at the answer tables or answer files for the 10 data sets, you can see that the width and the means of the 3 Gaussians are the same for all 10 data sets. And what's different is their relative amplitudes. And of course, each data set is fit with its own depth and background factor. This corresponds to the first model in the table. So I've already done that fit. It's completed. We'll take one look at the distance distributions for all 10 data sets. And let me just quickly show you the data set, the data panels for some of the data sets. Okay. All right, so this is that first model in the table. Let me go ahead and save this. And at a number of points throughout this particular video, I will pause the recording because some of these operations, 10 data sets, a large number of parameters, will take a long time. So I'm going to save this as PGP underscore model underscore 1, and I'll pause the video. So we finished saving that model number 1 for the PGP data. I'm going to go ahead and now increase the number of Gaussians to 4. We're still going to use that same linking where the depths, the backgrounds, and the amplitudes are not linked. The means and the widths of the Gaussians are linked. So if I look at the answer files, you can see a 4th Gaussian has been added, and it is going to be linked across the 10 data sets. We'll go ahead and run this fit, and I will again pause the video. So this second fit has finished. I'm noticing that actually gives a slightly different reduced chi-squared and slightly different BIC value than is in the paper. I'm going to go and look at the answer files. And I noticed that this one mean value is at 49.9994. So it is right at the upper limit that I've set of 50 angstroms. So what I want to do is increase that upper limit. And I'll go ahead and set it to 60 angstroms. I'm going to initialize. And let's look and make sure, but notice that that upper limit has changed for all of the other data sets because that parameter value is linked. Let's see, yeah, it is this one here, the R0_3. It's linked across all 10 data sets. So when I changed the upper limit for the first data set, it changed them for all the other data sets also. I'm going to go ahead and rerun this fit, and I should get a very small reduction in the reduced chi-squared. Okay, so that fit is finished. The reduced chi-squared now is consistent with what's in our table in the Journal of General Physiology paper. It's table 4. BIC value is different by 0.1. I'm not concerned about that. It's really an insignificant difference. Let's look at the answer file, and you can see that the mean of that one Gaussian is moved from basically 50 to 51 angstroms. So that resulted in a slight improvement, very slight improvement in the fit. Let's look at the distance distributions for all 4 data sets. And you can see there's one short component. There's one intermediate component. And then there are these 2 components which are at longer distances. I'm going to go ahead and save these results as, we'll save them as PGP _ model _ 2. And I will pause the video briefly here. All right, so those results have been saved. We can look at the statistics panel and see that indeed the second model that we ran with 4 Gaussians has a lower BIC value and is preferred over the first model. In model number 3, we have a 4 Gaussian model in which the relative amplitudes of the two Gaussians at the longest distances have the same relative amplitude. So they go together. And we can do that by editing our answer file. I'm going to go in, starting with the second data set, and link that fourth amplitude across all 10 data sets. Let me go ahead and initialize that model. Notice that the number of parameters has now gone down to a total of 59. And I can scroll back through the different data sets and make sure that indeed the linking has been done properly. Everything looks good. I'm going to go ahead and run this fit and pause the video. So this third model is finishing up. Let's take a look at the distance distributions, and you can see that there's the short component, the intermediate component, the two long components here, and you can see that indeed it looks like their relative amplitude of those two long components is the same across all 10 data sets. You can look at, well, we're going to go ahead and save that, and again I'll pause the video briefly, save it as PGP model 3, save, pause. So the saving of those results is finished. We can look at the statistics panel view and see that indeed model 2 is still the optimal model. It has the lowest BIC value. We can go ahead and save all of those statistics by clicking on the Write Statistics button. I'll save those. And at that point, we are now finished with those three models in the table. It's table number 4 in the Journal of General Physiology paper. And thank you for watching.